the topic of learning new representations. And let's see, to summarize in 2 sentences what we've learned so far. Interestingly, neural networks, when you train them, get to have hidden layers that re-represent the input for the purpose of predicting the output. And that gives us one way of learning representations in a supervised fashion. And we also talked about unsupervised methods that reconstruct the input from the output. And PCA is the example that we gave of a linear a system that learns a linear projection of the input features to a different representation, which is where each feature in that new representation is a linear function of the original ones. And fortunately, that has good algorithms and doesn't require that we worry about local minima problems. So that's what we've talked about so far. And I thought today what I would like to do is go through a number of other approaches and a couple examples. We won't be going into the details of proving why each one of these things is a good thing. See some of the variety of things that people are exploring and using for learning different representations, and you'll get some feel of, and this is a very active research area. We're not covering all of the stuff that's going on in the field, but I thought giving a sampling of this would be interesting. So one topic I want to begin with is a topic which is pretty hot right now, called deep belief networks. It's a modern-day area of neural network research. And the idea is this. If we'd like to learn representations, we might, as we talked about before, I have to turn on my ink. We might, as we discussed before, use a neural network. We talked, for example, about that autoencoder network, the one that tries to reproduce at the output the same input we give it. But if we want to do that in a more, to give the network a chance to learn a more sophisticated representation than you can get with a simple logistic function, then we might want to train a network that has many layers of hidden units. And people have tried that. And one of the problems you get into if you try that is even worse local minima problems, because now you have an even more complicated network that you're trying to train. And so people call these networks that have many stages of hidden units deep networks for kind of obvious reasons. And there's some interesting work. I want to tell you about some work that appeared in the journal Science a couple years ago by Jeff Hinton and Ruslan, I always have to read this one, Salakhutdinov. And Ruslan is actually going to be here in about 3 weeks to interview for a faculty position at CMU, so you might want to come and hear his talk. Anyway, I want to show you some of the work that they've been doing. So again, their idea is if we want to train a neural network to learn very good codes, re-representations of complex data, then we're going to want to train it with many layers of hidden units. And here's an example of one they did train. And what you see here in the top row are the original images of face fragments that they've been using. So that's what they trained on, and so they gave that as input and had the network have to construct it as output. What you see in the second row is the reconstructed output for each of those faces. So you see, like, this one looks kind of like the input. So this is the reconstructed image at the output of the network after it goes through this network that I'm showing you. And what you see in the third row is what you get if you use PCA instead. And so they use this as an example to illustrate why PCA isn't always good enough. Learning representations of the data that are linear transformations of the input and lower dimensional might not give you as good an ability to encode the information and therefore reconstruct it as if you used an even smaller number of hidden units whose values could be more complicated functions of the input. Okay? And the numbers here mean the original image, I guess, was 2,000 pixels, and then they shrunk that down to 300 PCA components versus starting with the 2,000 and using at first 1,000 hidden units and then going from there to 500 and from there to 30 and back out. Yes?
How do you statistically prove that PCA is not as good as DB? I mean, you can see the picture, the construction of PCA is bad.
Right.
How do you know that it's 80% similarity versus 60% similarity?
Oh, you mean how would we check the reconstruction error?
Right.
Oh, the standard way, if you think about what PCA is minimizing, it's the reconstruction error measured by the sum of squared errors of the pixels. So what PCA is trying to minimize, subject to the fact that it's going to use a single linear transformation, is trying to minimize the sum over the pixels of the squared difference between the pixel value here and here. And
the thing is, even if it minimizes, even if it got bigger error, it doesn't mean the picture that you reconstructed looks more different.
oh, I see. So you're raising a question about why would we trust sum of squared errors as a good thing to minimize when what we really want to minimize is the quality of the we want to optimize is the quality of the reconstructed image, and we don't really know psychologically how our brains work on it. Is that your point? Yeah, I agree. And so we use sum of squared errors for two reasons. One, mathematically it's convenient because that's what PCA does. And when we train a neural network with backpropagation, we're training it to minimize sum of squared errors. And then two, well, I guess those are the two reasons. It's mathematically convenient. That's what the algorithms do. And the second reason is we don't really have an idea of, say we went to image reconstruction. We don't really know what are the properties of arbitrary images that we want to preserve. So it's not like we have a clear alternative objective. But I agree with you. If you get to image quality, psychologists who studied our behavioral response to different faces and measured whether we could still recognize the person might come up with a different objective than this. Okay? So the point of this slide then is just that, look, this network really is doing a better job of reconstructing those face images than PCA does, and therefore it's worth pursuing this line of work. Question? Comment?
It's a different performance because of the part, or at least partly because of the different angles of the face. Will that mean will DB and ARC still work better if they are of the right angle?
Good question. So if you didn't hear in the back, the question was, unlike the other faces we looked at in the last lecture, which were all aligned and centered in the image, these faces are rotated and translated, and we're seeing different chunks of them. And maybe that's part of the reason why it's harder for PCA than it is for these. And indeed, I think it is. And I think that's why they made up this set of test images to illustrate the value of their approach.
Some eigen from from different angles of the
That's
face.
right.
It's very difficult.
Right. So if you think about it, this comes back to the fact that PCA is doing only a linear transformation of the input data to construct its encoding. It's just linear is what PCA is doing. Whereas this neural network is doing nonlinear logistic functions and furthermore many stages of them, which gives it a much more expressive language for generating these hidden features than PCA got to use. Okay. Okay, so then that's kind of interesting that they were able to do this. Well, there are a couple things interesting. One is that it works better than PCA for reasons that we just discussed. And it's also really difficult to train a network like that with backpropagation because the gradient descent procedure works very, very slowly, and there are all kinds of local minimum problems. So they had to come up with a different training scheme, which we'll see in a sec. But before we do, I want to show you another example. In this example, the input is a set of images again, but each image is some digit. So there's an image, there was image of 2, and they had many handwritten digits. And I'm showing you a sample of 10 of them. But they had many copies of 2 written multiple times, so they're not all identical and so forth. And here what they're showing is for PCA, they used, I guess there were 784 pixels in the original image, perhaps, but they mapped it into 2 dimensions. And with the neural network, again, they started with that, and they mapped it down to 2 dimensions. And what you're seeing here are dimension 1. Let's call them x1 and x2. For PCA versus x1 and x2 for the neural network. And then each point in these plots is one copy of one of those handwritten digits. And each one has a different color. So what you notice here is that, let's start over here. What you notice with the neural network is that the green dots kind of separate out. Which one are green? I can't quite tell on my...
6.
Okay, the 6. Good. So the 6s really kind of live in their own part of this 2-dimensional encoding, whereas in this one, they're kind of smeared out through some region that shares with other digits. So in this sense, again, we're seeing that this deep network with the more sophisticated, more complex mapping from the input to the code can come up with a coding that more cleanly separates out these digits, and you would imagine that that's helping it reconstruct them better as well. Okay. All right, so 2 interesting examples that let us look at these encodings and reconstructions. And so now the interesting question is, how would you train such a network? And this gives us a chance to touch on a topic that I wanted to touch on the first time we talked about neural networks, which is, isn't this something like a Bayes network, but not really? And how can we relate those and so forth? So the way they train it, we'll come back to this slide in a second, but I just want to show the figure from their paper where they describe how they train it. So here's the network that we want in the end. It's going to take an image. It's going to go through these different stages. But the way they train it, and they claim that this gives them much better solutions, is first they just train chunks of the network that have just 2 layers individually. And in fact, they just train it one that goes from the image to a 2,000 feature coding of the image, and then another one that, and they just work on that one until those 2,000 features reconstruct the image well. Then they take the 2,000 codes that they get for the image, and they train another one that goes from the 2,000 down to 1,000. And they train just that network till it does it well. So they train these separate pieces. Then they put them together. And in fact, they use the same network, and that we'll get to why they can do this. But they end up using the same network to do the decoding as the encoding. And then, so then that gives them 1, 2, 3, 4 sets of weights, which they've trained here, and they do that to put together this. And then they train this thing as a backpropagation using our backpropagation algorithm. But now they've already initialized the weights to pretty good values, which gets them presumably close to the local minimum that they really want the network to settle into. So this is a kind of heuristic method for getting an initial set of weights that you can then fine-tune with the backpropagation algorithm, and that's what they do. And I'm not going to try to defend, and I don't think they could prove that this is the optimal way of doing it, but in practice it works pretty well. It's, what should we say? It's research in progress. Yes?
So, because I guess in the fine-tuning stage you still are getting captured on the local minima, is the number 30 and I guess the error in reconstruction created from that, theoretically, maybe it can capture perfectly everything, but we just can't get past the local minima to see that. So how do we know what the lower bound on acceptable, that last layer?
Of that last layer. Okay, so the question was, why 30 units in that narrowest layer? Why not 25 or 40? They don't report on that. I bet they tried out some different numbers. But, and we can ask Ruslan when he comes in a few weeks. But think about it this way. How few could you get away with? Suppose you have, I don't know how many training images they have. Let's say they had 10,000 training images, just to pick a number. Now, if you wanted to come up with a code, how many units would you need? Could you prove that, like, you'd need at least 5 or something like that?
Could you?
No, right? Because 1 will do. These are real valued units. And if you have 10,000 images, I can give you 10,000 different real values and therefore encode them with 1 real number. So these aren't Boolean codes. These are real valued codes. So, of course, just 1 number will do it. You can assign each image a different number, and now you're done. But then you also have the constraint that whatever code you come up with, whether it's a 1-dimensional or a 30-dimensional code, has to also be computable with just this many hidden layers of logistic functions. And I don't know whether or not you could do that to get down to 1 unit. So what I'm doing is I'm saying, let's decompose that question of how many units into how many suffice to represent could we come up with a code. And there the answer is, well, 1 unit will do because they're real valued. And then the other half of the question is, but it has to be a code that's computable with this, within this representation. Yes?
So with the decoder, though, when it's decoding, that's just to get the information essentially back in the form that you started with, right? You're not reintroducing, smoothing, maybe in the decoding step to try to produce a better image. You're literally just trying to get it back into the same format. Is that right?
I believe that's correct. And there have been a lot of variants on this that people have been experimenting with, but that's my understanding. And I put a pointer to the paper here. Maybe I guess I could put it on our website too for more details. Uh-huh.
So in the step of the pre-training, when you train an intermediate layer, so is the objective the reconstruction error of the original image, or just the reconstruction error of that layer?
So for this first one, the objective is just to reconstruct the image because that is the hidden layer, or the input layer. But in the second one, it's just to reconstruct the 2,000 dimensional code, not the image. So these are done separately. and then they're put together later, and the entire system is trained.
Yeah.
So that's the heuristic.
The reason why you need a fine-tuning step.
Right, right. But their point was, you know, you might ask, well, so why don't we just start here? And their answer is because gradient descent does not work well at all on networks this deep, both because it's very slow, and furthermore, even after you wait so long, you end up in some local minimum that you can't control. So for reasons that they, to me, have not proven, but which empirically they claim turn out to be the evidence that they find, is that if you do it this way, it works much better, and then do a fine-tuning step. Right. So let's look at, I want to show you one more detail of this that's kind of interesting. It's a different kind of neural network than we've been talking about. It's similar in the sense that it's a completely connected neural network with just an input and an output layer. In fact, none of these networks that we're talking about training have a hidden layer. They're just simply an input and an output layer with weights between them. But the definition of those networks is a little different. Like the backpropagation networks, there are weights on all these edges, and we use logistic functions to calculate the output of the unit from the input. But their interpretation of these is a little bit different. So if you read the paper, they say, well, let's think about all these nodes being random variables, Boolean random variables initially, although later they extend that. Let's think about them being Boolean for our case. Then they say, well, we're going to define the semantics this way. Let's say the probability that the Boolean variable h sub j, let's take h sub 2, is 1 given the entire vector, so this is my notation for the vector v1 through vn, given the entire vector is just our friend logistic regression. This is the same thing we did when we did logistic regression. But then, interestingly, they say, we will also say that the probability for one of these v sub i's being 1, given the h's, is also a logistic function using exactly the same weights. And so when they train this to reconstruct the image, that's the network they're training. So basically, you input an image. Let's suppose it's an image, a black-white image, and it's ones and zeros, just to make the thinking simple. Then you can randomly generate a hidden code for that image by calculating the probability distribution on each of those hidden units, given the input v image, sampling that distribution. So now, you know, that just gives you a probability that each of the hidden units is 1. So then you sample that. You just assign them 1 or 0 based on that probability. And now you can take those Boolean variables, which are randomized, a probabilistic encoding of the image, and use them with this expression to reconstruct the image probabilistically too. And then, based on the error that you get there, you can update the weights and tune the network in that way. So that's the way they train it. This is called a restricted Boltzmann machine. It's a Boltzmann machine in the sense that it's a bunch of units, any subset of which you could observe, and the other subset of which it will give you a probability distribution over their values. And it's a restricted Boltzmann machine in the sense that this is a bipartite graph. There's just 2 layers of nodes, an input and an output layer, nothing else. But so they've come up with this kind of semantics for them, which is kind of interesting because it links now back to probabilistic interpretations of neural networks. So it's an interesting idea. So they train that, and as we discussed, they train these separately in that way, put them together, and then in the end they just train it as a big backpropagation network. So this paper is kind of interesting to look at because it has a collection of interesting ideas in it, including both the idea of learning representations, but also the idea of looking at a kind of probabilistic interpretation of what we've been calling neural networks. So there's a lot of interesting, and so now you can kind of imagine why there might be a lot of interesting work in this area right now, because probabilistic methods are very powerful. Neural networks are interesting because they can learn interesting representations. Maybe somehow if we put together those kinds of ideas, we could do even more. Okay, so that's really the end of what we're going to say about neural networks. As I mentioned, I want to sample a bunch of ideas. So in both these neural networks and in the PCA method that we talked about, basically we said, well, what we're going to try to optimize is the sum of squared errors in reconstructing the images. And then in the case of PCA, we further said we want a code that's an orthogonal basis in some lower dimensional space. Orthogonal basis just means that if I have three dimensions in my code, then they're orthogonal coordinates in a three-dimensional space. They're perpendicular to each other, which is not a constraint that the neural network has. There's another method that I just want to mention, which because it's quite often used, which, unlike PCA, principal components analysis, which looks for these orthogonal directions, ICA, which is independent components analysis, like PCA, learns a linear transformation of the inputs, but it seeks dimensions that are statistically independent. That is, where the mutual information between those, remember our old friend mutual information, here it is again, where the mutual information between the bits in the code, I shouldn't call them bits, what do you call real valued bits? The real valued bits in the code should be independent, have low mutual information. And so this turns out to be particularly useful, for example, if you have some noise in your data that's statistically different from the other variation in the signal. So here's a simple example where I've seen ICA used. People use it in brain imaging sometimes. Suppose that I have a sequence of brain images, somebody doing something, so I have a movie over time, a sequence of images of their neural activity. But there are external things not in their head that are causing noise. For example, we do imaging with magnetoencephalography, and every time a bus drives by, it causes noise because magnetoencephalography is picking up magnetic fields, very tiny ones that come out of your head, and buses driving by cause much bigger magnetic fields. So there's an example where we have some phenomena that's generating the signal, and then quite independently of that, we have these noise phenomena going on, like buses driving by. And so people often use ICA for that kind of application by saying, well, what we're observing are these images. We believe they have signal plus noise. Let's map them into some lower dimensional space again using linear transformations like PCA. So we get those same things like the eigenfaces that we had before, except that now, because we're choosing dimensions that are statistically independent, we end up, well, the noise is going to be statistically independent from whatever the person's thinking, the bus is driving by. And so they tend to get picked up by different components. And so then when you're done, what some people do is, you know, they look at the image, if you just reconstruct it from component number 1 or just from component number 2 and so forth, and in this way they can identify essentially noise. They can identify which of these components exhibit like no relation to the stimulus that you're giving to the person when you're brain imaging. And so it's probably just some external noise phenomena. Okay? So again, we're not going to go into the details of the math of how to do this, but I just wanted to mention this idea as another point in this design space of how could we set up systems to learn representations and what's an appropriate objective function. And so independent component analysis, like PCA, learns linear transformations, but different ones because the objective is different. Okay. All right. Here's another problem. This one's qualitatively different from what we talked about before. See, so I like the idea of learning lower dimensional representations for data, but if you want to run with the idea of let's get computers to learn good representations, then there are plenty of problems where we have not one data set, but several data sets that give us different views on things that are going on. And we believe there's some underlying single thing going on. Well, I'll give you an example. We might take brain image data from MEG, that magnetoencephalography imaging method, and then separately we might take brain image data from fMRI, which is a different, based on a different physics, based on a different instrument. But we believe in the end that those are just different views of the same neural activity that's generating those signals. And so there's a kind of prototypical example where we might have two very different sets of data. In our MEG data, for example, the raw data, we have 306 features per image, whereas in the fMRI data, we have roughly 15,000 features per image. So there are even data sets of different dimension. But we can collect them. And then we'd like to say, well, what we're really interested in is the neural activity, but we have these two different views on it. So why don't we get a computer program to learn a representation of that common underlying neural activity? And of course, what we have to give that program is simply these two different views. Okay? So that's the problem that's a different kind of representation learning problem, right? So far we've been talking about we have one data set, we want to learn a lower dimensional representation. And even more, well, I think cool, but an even more challenging problem is what if I have these two data sets and I want to learn a good representation that they can both be projected into? And now the question is, how do I want to define that problem? What's the objective function here? And how do I want to set it up? So there are two kind of popular methods for doing this. One is called generalized SVD, or generalized PCA sometimes. But basically, it tries to learn a representation that, actually, to be precise, I want to point out that the data we get from data set A and from data set B are paired in the sense that You know, if we're getting, let's say, MEG data and fMRI data, they're paired in the sense that we collect the fMRI data when the person's thinking about the word pen, and we collect the other data also when they're thinking about pen. So it makes sense to try to claim that they're both generated by some shared hidden thing. So given that, then one way we can define the objective is say, well, we just want to minimize the reconstruction errors of both of these. So we want some linear function that will map from data set A to here, and that allows us to reconstruct data set A. And simultaneously, we want to be able to map B into that and reconstruct it. But another approach is, which is called CCA. See, there's a tradition in this field. CCA, canonical correlation analysis, tries to maximize the correlation of what you get when you project data set A into this latent representation and what you get when you project B into it. Trying to make those as correlated as possible. And I want to dig into this CCA because we've been doing some work with this and found it to be very useful. A lot of people are exploring CCA these days. So let's take a more detailed look at CCA. Okay, first of all, it contains the word correlation. And so just to remind us what correlation means, correlation is a measure of how interdependent two random variables are. Suppose I have random variables A and B, and maybe I have, and there's some joint distribution P of A, B. And now I want to know how interdependent are those two random variables. So suppose I have, this is actually the sample, the estimate of the correlation. If I have n different draws of A and B, then what I do is I just look at the correlation is, well, this property is measuring for the ith observation, how far is A from its mean over all the observations. And it's normalized by its standard deviation. So this quantity essentially turns the random variable A into a zero-centered standard deviation 1 random variable. And then similarly for B, and then I just take the product of those two. So the idea is, think about it this way. Suppose A and B are random variables, and I have several observations. They're both centered at 0, and now in observation 1, I see there are these values. In observation 2, I see there are those values. They say, oh, they're moving together. They're correlated. The degree and distance from their mean that they vary, covary, is being measured here. So correlation is closely related to covariance. It's just normalized by these standard deviations. Okay, but essentially we're looking at how they covary, how they're correlated. Okay, so now let's look at what CCA is really trying to do. So suppose we have two data sets. Here's data set 1, and here's data set 2. And let's say each of those data sets, this is, I'm going to make this be observation 1. That's this vector. So X is, or X, has that many features. And on each observation, I get one column observed. And here is data set 2. And this is observation 1 for it. And, Y even has a different number of features than X, but we don't care. And so we have these 1, 2, 3, 4, 5 observations of both random variables. And so now we're looking for a linear projection of that data into a lower dimensional, in this case, one-dimensional space. one-dimensional space, a linear projection that will project this first observation into a single number. This is the one-dimensional space. And the same linear transformation will project the second observation into its number, and so forth. These are the 5 codes for the 5 observations when they're linear projected by just multiplying the observation, taking the dot product of that with the weights. And similarly here. Okay, so now I end up with these, whatever that linear projection. Now I'm learning 2 linear projections, one here and one here. But I want to learn those 2 linear projections so that they have the following property. I want this red random variable to be maximally correlated with this green random variable. And, you know, here my n is 5. I have 1, 2, 3, 4, 5 observations. Okay? So that's what I want. So one way to think about correlation is, if you want something to be perfectly correlated, 2 things to be perfectly correlated, the way to do that is to have one of them be a linear function of the other. That'll make them perfectly correlated. So in other words, CCA will be very happy if it can make this number identical to this number in all 5 cases. That'll be a very simple linear function. Or if this is just twice the number of the, 2 times that. It's a perfect linear function of it. Or if they're identical. So now think about it. That's exactly what we want, right? If this data was the fMRI data, and this was the MEG data, and I'm saying somehow there's some other space that we could transform that data into, and if we can find a space such that there's a linear transformation of this data into it and also a different linear transformation of that into it, where these are perfectly correlated, then we'd just be very, very happy. So that's the way CCA is defined in terms of objective functions. Uh-huh.
So my instinct just tells me it'd be really important to always run ICA over everything before you do it so that you separate out noise, because that'll probably have a really bad impact on this CCA step. If there's resident noise, and corollary to that is, can you take that too far?
So the suggestion is maybe we should run ICA over the data before we do this to try to pull out noise. Depends on the character of the noise and whether it's not as straightforward as it's not always straightforward to run ICA in order to denoise data, but people try that. So I like, in principle, your suggestion. In practice, it's an engineering problem. There's not a theorem that says you do this, then you do that. Yes?
Doesn't this, in effect, denoise the data?
This does, in a way, get rid of the noise. If I have different types of noise in the green and the red data, then, roughly speaking, I won't be able to make these things perfectly correlated. But if I try to maximize their correlation, then I should presumably have linear transformations that focus on the signal, not the noise, because, right. So this does, in a sense, squeeze out noise.
How would you define the objective function if the transformed data are not one-dimensional?
If the transformed data is not one-dimensional. Okay. So now the nice thing is we can talk about correlation between vectors of random variables too. So if I just make this a vector, if A is a vector of random variables and B is a vector of random variables, then correlation has the same definition.
But then it's not a scalar, it's a matrix.
Right, right. And so so I'm actually only showing you step 1 of CCA. Find the first canonical variable. And this is how we'll do it. Okay, so then step 2 is find the second canonical variable. And essentially what we want to do is subtract out the effect of what we can explain from the first one, and then learn a second variable on the residue. That's also achieving this maximum correlation property. So CCA actually can learn k-dimensional, n-dimensional, by just repeating this process of finding a coordinate that a single coordinate that gives you a maximum correlation, subtracting out the data that essentially is explained for that, and then finding another one
Yeah, it's
that's uncorrelated with it.
like a really step-by-step process. But on the whole, what is the objective function that this entire process tries to maximize?
Yeah, the objective function really is to find a mapping to an n-dimensional space that where the projected data points, the correlation of the projected data points is maximally correlated. That is the objective function.
So the objective maybe is defined as some function of the covariance matrix, maybe the trace or something. Or
Right, you can use the covariance matrix to solve for this, since covariance is so closely related to correlation.
yeah, but the objective function needs to be a scalar, so we need to transform the covariance matrix into a scalar.
Ah, right. So the objective function does need to be a scalar. And you're right. So what I just said would give us a kind of vector of correlations.
Yeah.
And short answer is I don't remember. Yep.
Oh, sorry, maybe I missed this. My question I have is, so say you have, unlike data like pixel value, intensity values, voltage readings, for example, how do you find the transform that actually projects the space?
Right, how do you find these W's?
Correct.
Right, and so there, you solve for it. And we're not going to go into the details of that. But there are packages that can do this, and it's basically a matrix algebra, linear algebra problem to solve for it.
Wouldn't you have to know what space you want to be in at the end then?
What you do, because this is a staged process, you find the first coordinate, then the second one, then the third one. Typically what you can do is just continue until you have as many dimensions here as you had in here, or just go until, because you're first solving for the one that captures most of the correlation, each additional incremental dimension you add buys you less and less. And so at some point you can just cut that off. Okay?
So you mean it's just like something like PCA that it will give you a serious number and you pick the the biggest first severals and you choose them.
Exactly. Yeah, in the same sense that PCA would give you as many dimensions, you'd project into as many dimensions as you started with, or actually the minimum of that and the number of data points you have.
So in that sense, we do not have to decide how many, and we have to do. We just could compute it and choose the first largest number.
Exactly. So just like PCA, a typical way of doing this is you get the components and you might get them all and then just sort them and say, I don't care after the 10th one. It's such a small effect at that point. Or if it's the staged thing, you can just cut off the search for additional ones. Okay. So again, I don't, there's, in today's lecture, what I want to do is just kind of sample a bunch of things, talk about the objective functions, why they exist. But for any one of these, I'd be happy to point you to papers on that give the details of the algorithms. And so part part of what I'm doing here is that I want to show you a bunch of stuff because maybe some of this will be relevant to your projects. Okay, so let me show you a project where this is relevant. So Indra Rastandi, a PhD student in our at CMU who graduated last year, actually did a PhD thesis where CCA was a central part. And I want to give you a little 5-minute summary of his work to give you an example of where this stuff can be very relevant. It comes from brain imaging world. We were interested in the problem of predicting fMRI images, brain activity, when people think about different words. We wanted to have a computer program that could do that. If we could have a computer model of that, then we'd understand something about how the brain represents meanings of things from neural activity. So we built, whoops, let me skip that. Oh, I guess I won't. And here are what the brain image data look like. So here's, for example, on that top row is the raw brain image data when a person looks at that stimulus up in the right corner, a bottle. So we put people in the scanner, we show them stimuli like that, and then we get brain images like this. It looks like I'm showing you 4 images, but I'm actually showing you part of one 3-dimensional image. Your brain is in 3. And so what I'm showing you are 4 different slices of one 3-dimensional brain image. And just to help you, this is the back of the head up here, posterior. This is the front of the head here, anterior. And as the thermometer says, red means high neural activity. So this person has lots of blotchy high neural activity in the back half of their head when they see this stimulus. So that's the kind of data that we're looking at. Each of these images has roughly 15,000 3-dimensional pixels, voxels we call them. Okay, so that's the data, and we want to predict those images that we'll see when we give somebody a particular noun, and we want a computer model that can be trained. This is what Indra's work was around. We want a computer model that can be trained to predict the neural activity that we'll see with fMRI for an arbitrary noun. Okay. So we built a model which did not use CCA at first. I want to show you that model, and then I'll show how CCA comes in. So the first model works this way. You know, the hard part about building a computer program that you're going to give it an arbitrary word is most computers don't know what arbitrary words mean. So what this model does is the first step, if you give it an arbitrary word like telephone, it first looks it up in 1 trillion words of text provided by Google, and it gets statistical properties of that word. Like how often does it occur with the verb eat, or the verb listen, or the verb speak, or the verb hug, and so forth. So then it gets these features. Those blue features are co-occurrence frequencies of the input word with different verbs, and that is its summary of the meaning of the word. It's its approximation to the semantics of the word. And then in the second stage, there's a huge linear regression problem. Actually 15,000 of them, one for each location in the brain. The model predicts the activity at each of those 15,000 locations by doing a simple linear regression, regularized linear regression from those features to predict the activation at that location in the brain. So that's the model. And you can see how you could train this if you had examples of words and what the fMRI images really were. You would take the words that you have in your training set, you look them up here, figure out what feature values they have for the blue stuff, and then train your linear regression system. That's what we did. And just to show you how that works, here, for example, if we have the word celery, we actually gave it a set of 25 verbs that I just made up. You can see celery, for example, occurs a lot with eat and a lot with taste, but not very much with ride. Whereas airplane occurs a lot with ride and not very much with manipulate. Okay, so that's the sense in which these corpus statistics capture something about the meaning of the word. And then the model predicts the activity at each location in the brain based on those numbers. So we just saw that celery occurs 0.84 with eat and 0.35 with taste and so forth down the line. So it's going to predict the activity at voxel V in the brain. This 5 features, the verb co-occurrence frequency. So summing over those 25 features, it's the feature giving the co-occurrence frequency of verb I with the input word celery times some coefficient that tells how much verb I contributes to voxel V in the brain. And these are the learned regression coefficients. Okay, and there are a lot of those. Okay, but that's the model. So that, you could have done this, even at the midway point in the course, right? We've done linear regression. This is a very simple use of linear regression on a large scale. Okay, now, yes?
So were the verb brain images, you had to collect a bunch of them, I assume?
So the question is, where did you get the verb brain images? We didn't. The training data is only of the form, here's a noun, and here's the fMRI image. Here's another noun, and here's the fMRI image. We never collected data where we showed people verbs. These images are actually images where each point is the coefficient that was learned in the regression. So these plots are actually plots of the learned coefficients associated with each verb for each voxel. Okay, so again, we train the system. We have nouns and images. So we get the noun. We look up those feature values, like 0.84 for celery and eat. And then we say, well, you know, celery is 25 features, and their values are 0.84, 0.35, etc. Then the linear regression gives us all these coefficients, and this plot is really a plot of those coefficients. Okay. All right, so that's the model, and it kind of works. Here's what happens if you ask it to predict celery in an airplane when it never saw them during training. The top row shows the images that it predicts. The bottom row shows the images that it never saw, but that are actually the images from this same person for celery in an airplane. So you see, it's not getting it perfect, but there are kind of gross features that it's actually predicting. Okay, so this kind of works. So we could be more quantitative by asking, we could test it, and did, in the following way. We had 60 nouns worth of data. So let's leave out 2 of those, train on the other 58. Then after it's trained, we'll show it the other 2 words. We'll ask it to predict the images. And then we'll say, well, here's the 2 real images for celery and airplane. Which one is celery and which one is airplane? And its way of deciding that is it looks at its own predicted image for celery and airplane, and it decides if there's a better correspondence by calling that one celery and airplane or the other way around. Okay. All right, so if it does this at chance, if it's just guessing, it's going to be right 50% of the time, just by guessing, flipping a coin. And in fact, this model was right 79% of the time. So it's not perfectly predicting the brain activity when you think about an arbitrary word, but it's doing it well enough that if you give it 2 words it's never seen, 3 times out of 4, it can tell you which of the 2 words was which. All right. So this is kind of an interesting model from a neuroscience perspective. But if you think about it for a second, the assumption this model is making is very strange. It's assuming that any thought you can think, or any word you can think about, any noun you can think about, the neural activity in your brain when you think about that noun can be predicted as the sum of 25 eigenimage components. You have 25 dimensional thoughts. That's what this model is saying. I don't want to insult you. I don't think that's the case. But it does raise the question, why on earth would we believe this is the correct model of how the brain represents word meanings? Why these 25 dimensions? Maybe you have higher dimensional thoughts. Okay, so we got interested in this question for obvious reasons. And we tried a bunch of things. A lot of friends advised us on what we should try. So instead of using 25 verbs, we used more verbs, 486 verbs, but that didn't really improve the prediction accuracy of the model. A bunch of things didn't. Actually, latent semantic analysis is interesting because this is a PCA-based analysis of a large text corpus that gives you 300-dimensional representation of the meaning of any word according to some PCA analysis. So we did try that. That didn't help either. But what helped the most is 20 features discovered from the data and using CCA by Indra's program. So let me show you Indra's model. So here's what Indra said. He said, oh, I need to tell you one other thing. While we were poking around looking for better features, this is a little entertaining, looking for better features, we found Dean Pomerleau. Remember that name? He was the guy who made that picture of the car driving, the neural network for driving the car. Dean Pomerleau, who a friend and a collaborator on this project, came in one day and he said, I just went to 20questions.net, and that's what we've got to use. So there's this great website called 20questions.net. You can go there and you say, I'm thinking of a word, and it asks you these questions, and after 20 questions, it guesses your word. So he said, we got to use those. To make a long story short, there were legal problems using their questions. Dean made up some. We used those. He made up 218 features. Like, is it bigger than a bread box? Is it shiny? Is it alive? Would you hug it? Stuff like that. Those 218 features, then he gave our 60 words plus another 1,000 to people on Amazon's Mechanical Turk. He said, here's some words. Here's some questions. Please answer them. People did. And so now we have, for each of our stimulus words, we have the answers to 218 questions. And those 218 did work better, 83% accuracy, than our original 25 verbs. Why? Probably for two reasons. One, it's probably spanning a larger semantic space than the 25-dimensional space that our verbs spanned. And two, humans were answering those questions, and so we weren't subject to a problem we had with the corpus statistics, which is that words have multiple meanings. And if you have a verb like see and a word like telephone or a word like hammer, let's take the word hammer, our program would check for different verb tenses co-occurring with hammer. See, saw, okay, so look for both saw hammer, see hammer. But unfortunately, saw is a tool. And so saw occurs a lot with hammer, but not because you see hammer a lot. So we had that problem with the corpus statistics too. So I think there were a couple reasons this worked better. Okay, but I had to tell you that because Indra's model piggybacks on that. So here's Indra's model. So he built a model that unlike the first model, which only applied to a single person, we'd train the model for a single person's brain. Indra said, well, I'm going to combine data from multiple brains, multiple data sets. These will be different people. And in fact, we had data with 2 different types of stimuli. We showed people the same 60 words, but sometimes we showed them the word only, and sometimes we show them the word with a picture, like that bottle picture with bottle written under it. Okay? But now, CCA. Here's where this comes in. So he built a model that he trained in 2 steps. First, he took, think about our CCA component. So CCA again, we have these 2 data sets, the red one and the green one, and we're looking for a linear projection of those into a lower dimensional space that maximizes the correlation between the projected points. So imagine I just had 2 different people looking at the same 60 words. So both data sets have 60 points. And so now I just try to find 2 linear mappings from those 2 people to a common representation of their neural activity. That's where the CCA comes in. So the first thing he did was he took not 2 but 20 data sets. He used a more generalized version of this to learn a 20-dimensional representation with CCA that maximized the correlation that you would get if you used the corresponding learned linear projection from these 20 people, 20 data sets. And so that gave a person-independent characterization in some space that we really don't understand of components of neural activity across people when they look at these 60 words. And then the second step for training his model was simply, how do we get from the input words to those 20 latent features? He just used linear regression. So you take the word, he looks them up in Dean's Mechanical Turk feature set. Is it shiny? Is it bigger than a bread box? And so forth. He codes the word that way. And then he trained a linear regression to predict each of these features, each of his 20 20 hidden features that he had learned with CCA. So you see, it's kind of a nice combination of 2 things that we've talked about in the course. So he used the CCA to learn this person-independent abstraction of neural activity and how it varies when you look at different words. And then he used linear regression to predict what those what the code would be for any given word. When you put that whole thing together, then he got 87% instead of our measly 79% earlier. So a very substantial improvement in the accuracy of the model by using this idea of getting the computer to learn the representation. So now this is pretty interesting, because now we're saying, no, really your thoughts are really only 20-dimensional. But that's okay. Earlier in this lecture we proved that they're really 1-dimensional anyway, if you just... So the 20 shouldn't scare you as much as it might. So that's what he did. Now, a typical thing to do, yes?
Did you try it for like more complex thoughts like emotions or violence?
Yes, we do. So the question is, do you try it with more... these initial experiments are all with concrete nouns, objects that you can touch. But we have tried it with emotions. We've tried it with words like love and hate and anger and anxiety. It works pretty well. Emotion words particularly work well. Not with these features. You have to... These 20-question features are about concrete objects. But you have to change the feature set to like word co-occurrence. But for emotion words, it works pretty well. We also tried very abstract words like justice and democracy, and that was not so good. Especially, I think we probably all have a different notion in our head when we think about justice or democracy or something. So, but in motion words, it really did work quite well. And we're pushing this in a lot of different directions right now. But one is to look at, like, what if I say to you, hammer, or what if I say 5 hammers? What if I say 8 hammers? What if I say cat, or I say sleepy cat, or angry cat? So what happens when you put words together and stuff? So there are a whole bunch of very interesting sort of cognitive neuroscience questions here. But anyway, I just wanted to bring this up as from the machine learning perspective. It's also so cool that you see how machine learning really plays a key role here, because it's the thing that's coming up with what is the 20-dimensional space in which your thoughts lie, at least your neural activity with regard to concrete objects. And that's essentially what this system is trying to solve for. Yes?
Do the person who you did the test on know all the words?
Yes, these are very common words like hammer, house, toe, tomato. Everybody knows these words, and they're unambiguous.
You didn't try some, weird something.
Well, okay, I could see where this is going. That's exactly what we tried when we started. So the first time we did this, we thought, this isn't going to work, is it? We were thinking, we were asking ourselves the question, could we train a classifier even to decode from the neural activity what word you're thinking? We're thinking, this isn't going to work. So let's pick really hard words so that people have to think really hard, and we'll get a lot of neural activity. So, so this is Marcel Just is my collaborator in this. So we sat down and we were like writing down these words like, oh, estuary, that's a great one, estuary, we'll do that. And so like we wrote down these words, and then we gave them to people in the scanner, and it was like, they didn't even know what estuary meant, right? And then Marcel asked me, what does the estuary mean? And I wasn't quite sure either. So anyway, then we did try that actually, and it wasn't such a good idea because the neural activity we got was probably as much confusion as anything.
At least you can predict whether the person is confused or not.
Right, and I think you can. Actually, that's a pretty interesting one. So I think you can predict whether they're confused. Okay, so one more thing about CCA before we put this down. Once you've trained a CCA system, or a model like this, then the obvious question to ask is, well, it's all very nice, this makes more accurate predictions than your previous model, but what are those 20 dimensions? What do they really mean? See, before I could say, well, they're verbs. They're verbs like see and taste and touch and hear, and we all know what those things mean. But here I've got, I can show you these 15,000 learned weights, and I will in a sec. I can, plot those weights right on the brain image so we can see where in the brain is component number 1 here, suggesting that there will be activation. We could do that. Another thing we can do is we could ask, among different words in English, what are the words that most activate dimension I? So we could rank, for any given dimension that we pick, we could ask, what are the words that most activate it? And then we can ask, where does it predict that there will be neural activity? So those are the two kind of things you want to look at if you're trying to figure out what those blue dots are representing. So this is what it looks like. So here are, for the top 4 components in the CCA model, so the 4 that explain most of the data, here are, out of the 60 words that we showed people, here are the 5 words that most activate component number 1 versus component number 2, 3, 4. So based on that, I'm not exactly sure what they mean, but my guess, and my guess is this first one means something about, you might call it shelter. The second one is stuff you can manipulate. All of those are things that you use your hands for. I have no idea what the third one is.
People write on.
I have no idea. And this might be things that touch my body.
Glasses, yeah.
Glasses. Yeah, I don't know. So and you have to realize there's a lot of noise in this brain image data. So the fact that you get groupings like this at all is kind of interesting. So we actually did the following. We actually went forward and we made up names. Actually, in another version of this, there's also one where there are a lot of edible things in one of the components. So we actually made up the name shelter, manipulation, and edibility. Oh, there's also another one. In fact, this might be what component 3 is, which is the number of characters in the word. I think that's probably, oh, no, that's not component 3. There's another one where all of the words that have a lot of characters excite that node, and all the words that have short ones don't. So anyway, at one point we took these presumed definitions. We actually took shelter, manipulation, and edibility. And then we got some people in a room, and we just showed them words, and we said, rate the words by shelter, how much they make you think of shelter, manipulation, and eating. And people did. They wrote down numbers from 1 to 7. And then we took those numbers and plugged them in as the values for the code for that dimension. And the predictions were very good. They were almost as good as if we used the linear regression to predict those. So that was kind of a corroboration that our guess about what the meaning was related to what it really is. Okay, so the final thing I want to show you is, okay, so this is from the word side. We can look at a component and we ask which words excite that component. But we can also ask what parts of the brain does this component point to? And so then if you ask that, you get this sort of thing. So here's for one component. This is a picture of a three-dimensional image of the brain sliced up. And so here you see for that one first component, the one that we were calling shelter, here is the projected, those are the linear weights and the linear transformation between the latent variable and the observed brain pixels. So the most interesting thing that came out of that final thing is this is the projection in the model. Remember, in CCA, you learn a different projection from each data set. So here I'm showing you just one of those 20 data sets. This is the projection from component 1 to it. It turns out another one of those data sets was the same person, but this time looking at stimuli that were words and pictures, and then the same person was another data set, but looking just at word stimuli. So it's kind of interesting to look at that person's projections in the two data sets, same person, when the only difference is whether a picture was included in the stimuli. And here's what that one looks like. So there's word only. Here's word in picture. There's word only. Here's word in picture. And remember, this is the back of the head. This is the front. And what you notice mostly is that the activity near the back goes away. The activity in the front is largely unchanged. Back of your head is where your visual cortex is. So okay, so let's end there. The moral of the story is here are just some examples of work going on around the question of how can computers learn useful representations. More next time.